everyone. Questions or anything before we begin? Um, I think I hope most of you have posted your homework 1 part 2, and then well, if you've not, try to do that as soon as possible. And of course, homework 2 is up on the web. As I mentioned in my email, we'll have quiz 1 this coming Monday, and I'll send out a separate announcement about that as well. And I've posted a sample quiz for you all to look at, basically the quiz from last year. So do make sure you try to understand all the material related and time yourself when you're doing that. Rebecca?
So I have a question on homework.
Okay.
And like kind of like applies to
Sure.
in general. Of like, for example, the very last like part thing of like problem A has you it's like UI, TIK, SIJ,
Right.
and it says like
Evaluate that expression, right?
So I understand like okay, so you have 3 dummy indices equals a triple summation.
Correct.
Is there like is the point of that to say like okay, it's a triple sum? And then the only way to solve it is to expand all 27 terms? Or is there like another way?
Sure, I think that's a common question, so let me try to address that. I think you're talking about UI, TIK, is it S, SKJ, and VJ, right? So this is an expression in indicial notation where you clearly see that I's are repeated, K's are repeated, and J's are repeated. That immediately should tell you that indeed there is a triple sum over each one of those indices I, J, K. So explicitly, if you were to write that out, you would have J is equal, I is equal to 1 to 3, J is equal to 1 to 3, and K is equal to 1 to 3. So a total of 27 terms, indeed. Now, one way is, as you pointed out, is to try to expand all of those terms, 27 terms, and have a plus there and actually compute it. And the result would be a scalar because in this expression, there is no free index, right? So there can be only one possible resulting value of all of this. When there is a free index in an expression, for example, if I have a free index, let's say I in the expression, then that expression might have 3 possible values. For I is equal to 1, 1 value. For I is equal to 2, 1 value. I is equal to 3, 1 value. In this case, I don't have any free indices. So there can only be one possible resulting value, which would be a scalar. Now, for expressions like this, if you have to evaluate expressions like this for a given vector component U, given tensor and tensor components for T and S, and given vector V, then you have to, maybe an easier way would be to try to interpret how these indices are working with their adjacent terms to try to figure out what that would look like in terms of matrix operations. Okay, so for example, if you look at something like this that we covered last time, TIK SKJ. If you look at this, if you remember, we said TIJ or RIJ can be written as TIK SKJ, where K is being repeated here, right? Maybe I have some of that pulled up right here. So if I have 2 sets of matrix components, 2 tensor components, and if I do a normal matrix multiplication of this matrix with this matrix, I get a resulting matrix R. For that resulting matrix, any component, IL component, can be given by Sij, Tjl. So this second index of the first matrix and the first index of the second matrix must be the same, and it should be repeated, right? So when we have that sort of an operation, that amounts to a matrix multiplication. So in the same way, you try to interpret what this expression is doing. So I just told you that you can calculate the result of this operation as a matrix multiplication of T and S. What would be the, so let's say I could modify that to call it UI, RI, J, and VJ, right? So one way to simplify that is to do a matrix multiplication of T and S, and you would get this sort of an expression. Can anybody tell me what you would do next to this? Yeah, you can choose to do something like combine these two together. What does that mean? It's a matrix times a vector. Again, because the second index of this first matrix and the only index here are the same, which means a summation over J. So we've seen that this type of an operation represents a matrix vector operation or a tensor acting on a vector. And I'll show you that right here. So a tensor acting on a vector gives me another vector, right? So Tij Uj gives me Vi. That's exactly what we're talking about there. So Rij Vj would give me some vector. Let me call that vector Wi, because I is the free index within this red box here. So I better have something that looks like Wi. And finally, you would obviously, you know what Ui Wi means, right? Ui Wi is U1 W1 plus U2 W2 plus U3 W3, which is a dot product of U and W. So if you were to think about it, this entire expression can be written as T acting on S, acting on V. All of this results in a what? In a scalar, vector, or tensor? A vector. And that vector dot product with U is basically what this expression means. So for expressions like this, try to interpret what it would be in terms of matrix and vectors, and that would make your computations simpler. But at the end of the day, you do have to sum up all of those 27 terms. It's just that arranging them in terms of matrix vector operations would be easy and more convenient. Okay. Any more questions? All right. So let's jump back to where we were last time. Let's see. So very quickly, we had talked about these tensors, how they act on vectors, what are the properties of these tensors, and then we talked about something like that we need often. We talked about the change of coordinate system, and that's important because I've been pointing out again and again that scalars, vectors, and tensors, these are all physical quantities. They do not depend upon the choice of coordinate system. Each one of you could have your own independent coordinate system and be describing the same physical quantity. So in order to talk within amongst ourselves about the same physical quantity with possibly different coordinate systems, we need to come up with a way to convert one set of components that refer to one coordinate system to another set of components that refer to another coordinate system. And we saw that this process of conversion between different coordinate systems is very easily captured by this matrix of numbers Q. And so this Q matrix is a transformation matrix that allows you to go for a vector. If you know the prime components, you just multiply with Q transpose and you get the unprimed components. If you know the unprimed components, you multiply with Q and get the prime components. So that was the transformation that we did for vectors. And keep in mind, the definition is very precise here. You have to be very careful with the definition. Qij is equal to E prime dot with E. So the first index, I, is always associated with the primed basis vectors, meaning these basis vectors. So, and the second index, J, is associated with the unprimed basis vectors. So if I'm trying to find Q11, I will take E1 prime and dot that with E1. That would, in general, be a non-zero or some number between -1 and +1, right? That would be cosine of that angle between E1 prime and E1. And similarly, you can come up with all the other 9, all the other 8, so total 9 values of Q matrix just by doing the dot product of the prime vectors with the unprimed vectors. Once you have that matrix, we also looked at how you would convert tensor components, because just like vectors have 3 components, tensors have 9 components, right? So as I mentioned, if you have these 9 components of a tensor in one coordinate system, the exact same tensor can have 9 different components in a different coordinate system. And now that we know how to convert vectors between one coordinate system to another system, we can use the same logic to convert tensor components. So for example, if I'm given T prime, I can post multiply with Q and pre-multiply with Q transpose. That will give me another 3 cross 3 matrix of the unprimed components, and vice versa. If I know the unprimed, post multiply with Q transpose, pre-multiply with Q, and I get the primed components. So that's how you would convert tensor components between two different coordinate systems, right? So that's about where we were last time. Any particular questions about any of these conversion processes? So I think one of the homework problems on that you have does ask you to convert between these two different coordinate systems. So once you try that, hopefully things will be more clear, more concrete with a specific example in front of you. But of course, I have office hours after the lecture, and you can ask me questions if you need. So let's go on with more properties of tensors and vectors in general. We are talking about tensor invariants. Okay, what is an invariant? It's something that does not change if you change the coordinate system. So as I've said, scalars, vectors, tensors, these are physical quantities. They don't depend upon a coordinate system. They don't change just because I choose a different coordinate system, right? So the physical quantity itself does not change, but its components change. So when we talk about invariants, we are talking about quantities that we compute using using a specific coordinate system. And if we were to compute the same quantity with a different coordinate system, those quantities would not change. Can you think of some quantity? For example, let's say I have this vector v. I have these two coordinate systems. Can you think of some property of v that would not depend upon the choice of coordinate system, no matter what coordinate system I choose? Say that again. The magnitude. Magnitude. Anything else? Well, yeah, I guess a vector has only direction and magnitude, right? So magnitude indeed is something that would not change no matter what coordinate system you choose. So if I were to write magnitude of v, one way to write that would be what? Dot product of v with itself. So v dot v. And in terms of indices, how would we write that? vi, vi. Where's my pointer? Okay. vi, vi. Let me ask you this. Can I write this as vi square? Why or why not? That's right. So we cannot write this in initial notation as vi square, because when we do that, we are removing one of the i's. And since I is repeated here, there is an associated sum, a summation I over 1 to 3 for this. That's why we get v1 square plus v2 square plus v3 square here. We cannot write that as vi square. If you want to explicitly write that as vi square, you would have to use the sum 1 to 3. So that would be like an exception. Then it would be okay, right? So then I can remove those cross lines. Now this is okay because I'm explicitly saying that there is a sum over I. I'm not assuming the summation convention. Okay. So in one coordinate system, let's say in E1, E2, E3, I'm writing this as vi, vi. Indeed, that is the magnitude of the vector. And since this is an invariant, I can express the same vector. I can express the same vector as vi prime, sorry, same magnitude as vi prime, vi prime. So this should work, correct? Actually, I need a square root everywhere. Magnitude of v is v dot v and square root, right? So magnitude of v is square root of all of that. So the objective here is to show that whether I calculate V1, VI or VI prime with respect to a different coordinate system, I'm going to get the same number, same scalar that represents the magnitude of this vector. How can I do that? How can I show that whether I calculate it using the prime components or the unprimed components, I'm going to get the same magnitude? That's right. So I have the primed components. I can find the unprimed components using Q transpose, right? So if I have the primed components, I'll convert them to the unprimed components using the Q transpose, and then I'll see if I end up with the previous expression. So I'll write it as square root of Q J, or let me say Q transpose J I, Q I J V J transpose, that's this, and another Q transpose I K V K prime. So what I'm doing here is I'm taking one of these primes and I'm writing it as Q transpose IJ V, let's be careful here. So the primed components don't have the transpose, right? Right, so primed components don't have the transpose, so I don't need to write the transpose here. So no transpose. And I don't need the primes. So all I did was took Vi prime and converted it to Qij Vj, and the same thing for the second one, that is Qik Vk. Now you have to convince yourself first of all that the substitution I made here is valid. I'm just substituting from the previous page of the primed components. Further, I changed something here. It was Vi prime, but I'm writing it as Qij Vj. Why is that? Because J here is repeated and the free index in this expression is I. So this free index and this free index has to be the same between this blue expression. Similarly, for this guy, I have K as the repeated index. Can I write J here? Can I write Vi prime is equal to Qij Vj? Why or why not can I just repeat this expression here? Right, the dummy index can occur only twice, which means if I were to use J here, I would have J 4 times, not allowed. Okay, and the handout that I just sent around for today has the notation rules, essentially, what is valid, what is not valid, examples of mistakes. So be sure to look at that, and you'll see that this would not be allowed, that you cannot have 4 J's in there. So indeed, what we have now is this. I can modify this expression. So starting with the prime components, I got this, and I can modify this expression as square root of Vj Q transpose J I and Q I K and Vk. Okay, so all I've done going from here to here is just switch the order of this. Can I switch the order of multiplication of Qij, Vj and Qj and all that? In matrices I cannot do that, but these represent specific components. Specific components of matrices are scalars. I can change the order of those components any which way I want. Okay, so going from here to here, all I did was made this transpose, so Qji, and switch the order of that. And clearly, you should be able to see that this quantity right here, Q transpose Ji, Qik, note that the second index here, first index here are the same, which means a Q transpose times Q matrix multiplication. What is Q transpose times Q? Identity. which is represented by the components of the canonical delta. So I would write that as delta j k, right? Q transpose Ji Qik indeed represents the identity matrix, and the components of the identity matrix are represented by the canonical delta. The first component here and the second component here give me delta Jk. Now I can simply contract out K, replace that with J, and what I get is square root of Vj, which is exactly the same thing as square root of Vi, right? I and J both are dummy indices, so I can replace that with Vi. So what we've done by doing this is to show explicitly that indeed the magnitude of a vector, no matter which coordinate system you use to compute, is computed exactly the same way. Just take the square root of the sum of squares, and no matter which coordinate system you use, it's an invariant. It does not change with change in coordinate system. So that's what an invariant is. And this concept of invariance is much more useful for tensors. So in tensors, you have, of course, these 9 components, which will change if you go from one coordinate system to another. We know how that change occurs, Q transpose before and Q afterwards. So you'll get these different sets of 9 numbers that represents the same tensor. So in tensors, what is invariant? Any function that does not depend upon the coordinate system, which would be written as if I have some function of the components Tij, if I can calculate the same components using the different coordinate system. So for example, if I use a different coordinate system is equal to Tij prime. So if I have a different coordinate system, I will have a prime set of numbers. If I calculate the same function using the prime components, I should get the same value. Exactly the same way that we had here. Magnitude with the unprimed and the prime components was the same. So that's basically the definition for an invariant. So maybe before I talk about these types, these different invariants, primarily there are these 2 types of invariants. One is called a primary invariant, and very shortly we'll see something called a principal invariant. So you have to be very careful about this terminology. One is a primary invariant, one is a principal invariant, and both are obviously invariants, but you need to understand how to calculate them. So the first primary invariant, F1 of the tensor T, is simply Ti. So if I give you a tensor with its 9 components, what does Ti mean? Sum of the diagonals, right? Why? Because I is repeated, so it means T11 plus T22 plus T33. So you give me any tensor, if I take the sum of the diagonals in one coordinate system and take the same tensor, convert it to a different coordinate system, I'll get T11 prime, T22 prime plus T33 prime. The sum of the diagonals in both those systems would be exactly the same. Okay, and this thing, which is basically the sum of the diagonals, there's a special name for that. We call it trace of the tensor T. Okay, and let's verify whether this is true. So we know for a fact that the primed components Tii prime are given by that change in coordinate systems formula. The primed components are given by the unprimed components and Q transpose post multiplied and Q pre multiplied, right? So you should be able to see that this long expression right here, Im Mn Ni, this essentially means a matrix multiplication of T with Q transpose and Q with the resulting matrix. And further, we are going to take the sum of the diagonals for the resulting matrix. That's what this means. Okay, let's make sure that this that this thing works. So what we'll do again is just rearrange this. Since these are all scalar components, I'm going to rearrange them as Ni, Q, I, M, T, M, N, right? And once again, this is Q transpose times Q, which can be written as, what would be the product of this? Q transpose Q, delta NM. That's right, because the first index here, so the second index here and the first index here are the same, that is I, which means the result would be delta NM, and I have TMN remaining. I'll contract any one of those. Let's say I contract N and replace that with M. So what I get is TMM, which is equal to TII, which is equal to TJJ, or whatever you want, right? So we have just shown that whether you use the primed components to calculate the sum of the diagonals, or you use the unprimed components to calculate the sum of the diagonals, that result would be exactly the same. So more explicitly, you have these two, the same tensor in two different coordinate systems. We know the relationship between these 9 components, right? We know the relationship between these set of blue components and these purple components is given by these two expressions. So if I take the sum of the diagonals here, T11, T22, T33, that would be the same sum of diagonals as T11 prime, T22 prime, T33 prime. And that's why it's an invariant. That does not depend upon the choice of coordinate system. So hopefully I've beat that into you guys. Let's talk some more about a couple more invariants. So these primary invariants, they have a nice property that you can create them arbitrarily, essentially, by multiplying the matrix of components with itself repeatedly, Tij, Ji. All that you have to do is to make sure that the second index here and the first index here is the same. In this case, that's J. And the last index here and the first index here are the same. That's I. So Tij, Tji, that is the trace, which is the short way of writing trace is Tr, T squared. What is T squared? T acting on itself. It's the composition of tensors. We also looked at composition of tensors, right? A tensor takes an arbitrary sphere of vectors to an ellipsoid of vectors, and the next tensor that acts on that takes that ellipsoid to yet another ellipsoid. Right? That's the composition of tensors. So T square is a composite tensor made out of T acting on T itself. And of course, if you have two 3x3 matrices of components of T, you do T times T, you get another 3x3 matrix. And the trace of that, the sum of the diagonals of that resulting matrix is what we are talking about here, F2. Make sense? So, so we'll use some of these properties. And finally, you can create more primary invariants the same way, Tij, Tjk, Tki, that's no surprise, trace of T cube, and similarly you keep on going that way, and what you get here, this last one is trace of T to the power n. Okay, so hopefully you should be able to see that there are n T's here, and if I do a matrix multiplication of T, or T raised to the power n, then at the end I will indeed get a 3x3 matrix. If I take the sum of the diagonals there, that would be the trace of T to the n, and that would be an invariant. No matter which coordinate system you choose, you'll get the same result. One quick thing to point out here is that since this is a 3-dimensional, we are talking about tensors in 3-dimensional space, only 3 the first three of these are truly independent, meaning all of the rest after the first three can be expressed in terms of the first three. So these three, for F1, F2, F3, the primary invariants are truly independent, but everything else is dependent upon those three invariants. All right, so that's primary invariants. And let's talk about the second type of invariant, which is called a principal invariant. So hopefully the word principal values also rings a bell for you all, maybe back from linear algebra. Every time you hear the word principal, it usually refers to eigenvalues and eigenvectors. Right? Principal values of principal stresses, principal strains, those are eigenvalues and eigenvectors of strains and stresses. So in this second type of invariant is called the principal invariant, and let's talk about what that is. The idea is that, as I've been saying, that there is what a tensor does is it takes this arbitrary sphere of unit vectors given by this red ball here, and it transforms it to an ellipsoid. In doing that, what a tensor usually does is it takes any given vector here. It can take that vector and stretch it and possibly rotate it. Okay, so that's usually what a tensor does to a vector. It can stretch it and rotate it to a different direction. But it so happens that for symmetric tensors, there are certain directions, three directions in general, that the tensor only stretches or contracts. It does not change the direction of that vector. So there are these three directions which are called principal directions. And I've denoted them here with, let's say, these three dark green arrows, n1, n2, n3. For these three particular directions, the tensor will only change the length or the magnitude of that vector. So if you go here, you can see that T acting on n2 gives me a longer n2. T acting on n1 gives me maybe a little bit shorter n1. T n3 gives me a longer vector. So for these three particular directions, there is no change in the direction, which means I can write that operation as T acting on a particular direction vector n is equal to the same direction vector n scaled by some scalar lambda. Okay. So T acting on n, on the left hand side I have a tensor acting on a vector to give me a vector. On the right hand side I have the same vector but scaled by some scalar. That's the definition of a principal direction n. And the associated value, the scalar value by which it's stretched, that's scalar lambda. That's the eigenvalue. And the idea is that to solve for these types of eigenvectors and eigenvalues, something that hopefully you are familiar with, we are solving for non-trivial solutions of this equation. If I take this guy to the left, I get T minus lambda I n. This is a new tensor acting on n is the zero vector. So just notationally, can I omit I here? Can I just simply write it as T minus lambda? No, because T is a tensor. I better be adding or subtracting tensors with itself, not a scalar. And on the right hand side, I have an underline under zero. It's a zero vector. It's not a zero scalar. Okay. So I need to look for non-trivial solutions for this type of an equation, which we know happens only when the components of this matrix give me a determinant equal to 0. So determinant of T minus lambda I should be 0, which gives me this equation. I just take the given tensor components, subtract lambda from the diagonals. That's what this guy is. Take determinant of that resulting matrix, and that will give me some equation in terms of lambda, right? What order of polynomial in lambda would that be? Third order indeed, because if I try to take the determinant of this, I would have T11 minus lambda times T22 minus lambda times 33 minus lambda and some other terms. which will lead me to something called the characteristic equation. This characteristic equation itself is an invariant. No matter which coordinate system you choose, you are going to get the exact same equation. You can express this tensor, 9 components, in this coordinate system, E1, E2, E3, or another E1 prime, E2 prime, E3 prime system. You are going to get this exact equation. What are these these coefficients here? We have minus lambda cube plus something called the first principal invariant, IT, lambda square, minus second invariant T, second invariant of the tensor T times lambda plus the third invariant. So since the coefficients of this equation are invariants, this entire equation itself becomes invariant. And let's in particular look at what this, so maybe an easy way to remember this equation is you obviously start with a minus lambda cube, because this times this is going to give you minus lambda cube, plus first invariant minus second invariant plus third invariant. Okay, and the definition of those invariants: first principal invariant is the same as the first primary invariant. You remember this first primary invariant was TII, trace of T. It's the same first principal invariant, so I'll write that as TII. However, the second invariant is different. Half of trace of T square minus trace of T whole square minus trace of T square. So in terms of indices, how would we write that if you were to write all of that? Clearly, let me ask you this: trace of T, what primary invariant is that? TII. Trace of T square, what primary invariant is that? TIJ, TJI, right? That's the second primary invariant. So I can write that as half of TII. And how do I get the square here? Can I write TII square? No. What should I do? TII? Yeah, so without using the summation also we can write it. TII and TJJ. I can't repeat I. Okay. So I and J both are repeated indices. They occur exactly twice. And indeed, this is trace of I. This is also trace of I. Put together, that is trace of T square. And minus the second invariant. So here I can reuse I and J now because this is a different term. But just to be clear, I will not do that. I'll write that in terms of KL, TKL, LK. Okay. So the second term here is trace of T square. And I'll show you examples of this also. The third invariant is a determinant of T. And yes, there is a long expression initial expression for determinant of T, which actually, if you look in the back of the book, there's an exercise problem to prove that determinant of T is indeed given by this long expression. But let me ask you this: how many free and repeated indices in this expression? How many free indices first?
6.
Free indices. 0 free indices. Which means what? Only one possible value it can have. Meaning that the result would be a scalar. Indeed, determinant of a tensor or determinant of a 3×3 matrix is a scalar. And how many repeated indices? 6. Which means how many totals? So since there are 6 repeated indices, there are 6 summation signs sitting up here. Sum over I, sum over J, sum over K, L, M, N. For each value of those we have, so this is a long sum. How many total terms in this sum? 3 to the 6. I won't even bother calculating how much that is. Right? 3 to the 6 terms in that summation. So indeed, that is not the way we calculate determinants. But in terms of indices, it is helpful to write determinant in this way because you're going to get these types of indicial expressions with everything else. And there are lots of good ways to work with these alternating symbols. You remember in these alternating symbols, there are 21 values that are 0. Another 21 values that are 0 here. 21 times 21, that is a lot of 0 values, right? So the only non-zero values that you would get would result in that determinant, okay? But so you might think that why do I want to use such a long expression with 3 to the 6 particular 3 to the 6 possible terms and sum them up? Yes, we don't do that. This is a shorthand way of writing the determinant of a t using indicial notation, because we are going to be using indicial notation for a lot of the other derivation that we do. Whenever we come across a determinant in that derivation, we can simply use this, and then since we're going to have to take derivatives of these scalar quantities or scalar fields, it will be easier to take derivatives of these things rather than a derivative of a determinant of a tensor. Okay. So anyway, we'll come to that. So these are just the basic definitions of the principal invariants. So again, two types of invariants, primary and principal. Be sure you distinguish them carefully. All right, so in the rest of the time that I have here, very quickly, I'll go through some of the techniques to calculate these determinants. So for example, if I have a tensor T, this is a very particular tensor, I want to calculate its principal values and its principal directions, which is exactly the same as saying calculate its eigenvalues and eigenvectors. So the first thing we do is to try to calculate determinant of t minus lambda I, and in order to do that, we would be equal to 3 minus lambda 0 0 0 and 5 minus lambda 0 0 minus 1 minus 1 and 5 minus lambda. So hopefully you are able to convince yourself that the determinant of this matrix, if I expand it about this element, would be 3 minus lambda, 5 minus lambda times 5 minus lambda minus, sorry, this should not be 0, it should be minus 1. Minus 1. So we get this expression. And indeed, we want to solve for values for which this is 0. I've done most of the algebra here, so you don't have to calculate all of that. You'll see that we get this equation where 13, 24, or 54 and 72 are the coefficients that you would get just by doing multiplication. This would be the first invariant, second invariant, third invariant. Excuse me. Let me ask you this. What would be the eigenvalues? Can you factorize this expression? That's right. So exactly, you can take this guy, what you have left here or here is a quadratic equation. If you factorize that, what you would get is 3 minus lambda, and the two factors of 24 that sum up to minus 10 are minus 6 and minus 4. So I can write that as lambda minus 6, lambda minus 4, or I could write it the other way, 6 minus lambda or 4 minus lambda, same thing. And indeed, if I do that, it gives me lambda 1 is equal to 3, lambda 2 is equal to 4, lambda 3 is equal to 6. So 3, 4, and 6 are the eigenvalues. What does that mean in terms of the tensor itself? It means that, I'll go back to the previous page. It means that for this particular tensor that we are talking about, there are 3 directions for which the vector will not rotate when the tensor acts on it. It will only extend by how many? By how much? By that eigenvalue, which is that if you pick the n1 direction, it will stretch by 3 times, n2 direction 4 times, n3 direction 6 times. So that sphere of arbitrary vectors will become an ellipsoid that is much bigger, 3, 4, and 6 in the n1, n2, and 3 directions. Let's find out what those directions are. So hopefully you all remember this, but the way to find eigenvectors is to basically solve an equation. Since we said that we are looking for non-trivial solutions for t minus lambda I equal to 0, we have to find non-trivial solutions for this matrix. So for lambda 1 equal to 3, if I substitute that in this matrix, I get 0, 0, 0, and 0, 2, minus 1, 0, minus 1, 2. Okay. Now, the way we do that is usually by setting one of these components to be 1. So, am I missing something there? No. Okay. So we'll call this component to be 1, and we'll remove the first row and the first column, and we'll try to solve for this system. I'm just checking if this is the same system. So this blue system is what we are going to solve. Why do we have to do all of this? Because if you look at the original black matrix, there is this and this, all zeros. So if you try to calculate or try to solve this system of equations, there will be infinitely many possible solutions. Okay. That's why to get a unique solution, we take one of the vectors to be 0 and cross out the corresponding rows and columns and get a reduced system, a reduced 2 cross 2 system. Now this system we can solve, and if you do that, there's a unique solution for that. You'll come up with V2 equal to V3 equal to 0 in this case. And I'll let you convince yourself of that. It's very easy to do. Just multiply the first row here by 2 and add them together. You will see V2 equal to 0 and similarly V3 equal to 0. So what that gives me is that this is 0 and this is 0. So that means that in one direction, and I should not be writing it equal to, in one direction can be represented as 1, 0, 0. That's the first eigenvector. Okay. 1, 0, 0 is the same as E1, right? 1, 0, 0 is the same as E1. So this particular tensor T takes any vector along the even direction and just triples its size. It does not rotate it, a vector in even direction. In the same question, go ahead. So as I said, that what we are looking for are trivial solutions to this problem. So let me do that for a second and I'll explain it again, okay? Here, we are looking for trivial solutions of this problem. So lambda, for the second eigenvalue, lambda equal to 4, I'll take that and take lambda equal to 4 and subtract that from the diagonal. I get -1, 1, and 1. Everything else remains the same. And I'm going to try to solve for non-trivial solutions for this equation. This equation, by definition, is singular. The matrix here is singular. So I will get infinitely many possible solutions. I can't work with infinitely many possible solutions. So just to get a unique solution, I'll pick one of the components to be 1. When I do that, you have to be careful. Let me ask you this. If I take this V1 again to be 1, and if I cross out the first row and the first column here, the remaining matrix 1, -1, -1, +1, is that something that's a what is the determinant of this sub matrix, 2 cross 2 sub matrix? 0. So when I did that, it's still a determinant 0 matrix. So you have to be careful that when you choose one of the components to be 1, the remaining matrix must not be a determinant 0 matrix. So to avoid that, what I can do then is to say that, okay, instead of V1, I'll say V2 equal to 1. And I'll move the cross out rows and cross out columns also to 2 cross 2. So if I do that, now my remaining matrix is -1, 0, 0, -1. What is the determinant of that? -1. That is a non-zero determinant, which means I can solve the system. I can solve the system -1, 0, 0, 1, V1, V3 equal to 0, 0, which simply means that that V1 and V3 should be 0. I think we should end up with V1 equal to V3. Am I missing something here? So, oh yeah, that's what I'm missing. So it's not equal to 0 because I have to, if I take the first row, I get -1, 0, V1 equal to 0. And if I take this, the third row, I have a -1 here, so that would multiply with V2 and go to the right hand side, which would give me -1 times V2 on the right hand side would give me plus V2, right? Plus V2, and so V2 would, or V3 should be, since it is plus V2, which is basically +1, therefore V1 and V3 are 0 and 1, right? And therefore the N2 vector, turns out to be represented with first term is 0, second term is 1, third term is 1. And to this 0, 1, 1 is not a unit vector. So just to normalize it, I will divide it by its magnitude. The magnitude of 0, 1, 1 is 1 over square root 2. And looks like I've gone way over my time here. So basically what we are doing again and again here is to calculate eigenvalues and eigendirections. And there are lots of other ways of calculating these eigenvalues and eigenvectors. I'll let you figure those out and talk more about it on Friday. But essentially, for the homework problem that you have, all you need to do is to calculate eigenvalues and eigenvectors of the given tensor. Okay. All right. So let me stop here. If you have more questions, I'll be happy to take them in my office hours, starting in 5 minutes.